Good afternoon. Welcome, everyone. We are so pleased to have you join us for the Sharing Ocean Acidification Resources for Communicators and Educators webinar series. Today's source webinar is presented by the NOAA National Marine Sanctuaries and Ocean Acidification Program, really on behalf of the many offices in NOAA, the National Environmental Satellite Data and Information Service, Office of Education, and National Ocean Services. Our goal is to provide ocean acidification communication tools to formal and informal educators and stakeholders across the country to promote a more integrated and effective ocean acidification community. I'm Jen Bennett-Mintz, Education and Outreach Coordinator with NOAA's Ocean Acidification Program, and I'll be moderating today's session with Laura Francis, the Education Coordinator at the Channel Islands National Marine Sanctuary. Thanks again for being here today. We've had over 275 folks register from all around the globe, and we are very excited that you've taken the time to join us. We would love to know a bit about how you spend your days. So you will see our first poll pop up that asks, how you spend your work days. So please answer by clicking on your choice. You can select more than one, and you can also choose other and tell us what audiences you tend to interact with, or if you don't fit into one of those categories, you can share that by typing into the questions box. The responses are coming in. We'll leave it open for just a few more moments. Looks like we have a great variety of folks on the line doing different things in their days. Okay, we'll go ahead and close this poll. It looks like we have, as I mentioned, a really good variety of people on the line. There are about a quarter of you who do conduct scientific research, 19% teach in a classroom, 40% teach in an informal setting, nearly 40% are communicating science in some way. And as we see some of the other options, we've got teachers on the line, some college programs, and folks that work in professional development as well. So thank you for letting us know that. Polls are one way we will interact during the webinar. During the presentation, all participants will be in listen-only mode. And you are welcome to type, just as you offered your current roles, you're welcome to type any questions you may have for our speakers into the questions box shown here that's on the control panel on the right-hand side of your screen. We'll be monitoring those questions and we'll respond to them and post them to our speakers at the end of the presentation. Also, we always welcome your input on who or what you would like to see as a future source webinar, speaker or topic, or any resources that you would like us to cover in upcoming webinars. If you have any ideas for that, you're welcome to type that into the questions box as well, and we'll take those into consideration as we plan for the future. We are recording this webinar, and this session will be shared via Google Drive with all of those who registered. And we will also be eventually posting this on the NOAA Ocean Acidifications Program YouTube channel. So the title of today's presentation is, on a scale of 0 to 14, how familiar are you with the ocean acidification facts? And we are very pleased to have two presenters to discuss this with us today. We have Dr. Kari St. Laurent, who's a research coordinator at the Delaware National Estuariene Research Reserve, and Amy Dean, who teaches biology and environmental sciences in the classroom and was an education lead in developing the NOAA Data in the Classroom module. A little bit more about Kari. Kari is an environmental scientist with the state of Delaware and research coordinator for the Delaware National Estuariene Research Reserve. She holds a PhD in oceanography from the Graduate School of Oceanography at the University of Rhode Island and is perfectly okay being a total science nerd. She is currently the state representative on the Mid-Atlantic Coastal Acidification Network Steering Committee and the co-lead for the National Estuariene Research Reserve's Coastal and Ocean Acidification Work Group. Amy has worked in science education for 20 years. She holds a master's degree in marine biology and is fascinated by the wonderful and bizarre world of marine invertebrates. She has been working with NOAA for 15 years, managing education programs, designing curriculum, and providing teacher training services. In all of that spare time, she is a full-time teacher of biology and environmental science for high school students in the San Francisco Bay Area. As a team, they will be presenting both the science behind ocean and coastal acidification and walking us through a brand new module of data in the classroom that is focused on ocean and coastal acidification. So without further ado, Kari, I am going to hand it over to you to introduce us to the science.
Perfect, and thank you very much for that introduction. Hopefully everybody can hear me okay and see my screen. And so I'm just gonna go on and get started. So hopefully after this short presentation, everyone will come out having an idea of how climate change is connected to ocean acidification, the chemistry behind what happens when atmospheric carbon dioxide enters into seawater, some of the drivers of coastal acidification, a few impacts of coastal and ocean acidification, and a few glimpses into the potential future. And I'll have some studies sprinkled throughout.
Kari, before we move, should we find out how familiar folks are with coastal and ocean acidification?
That is a perfect prompt. Go for it.
So we have another poll. How familiar are you with ocean and coastal acidification science? Extremely familiar, very familiar, somewhat familiar, not sure. I haven't heard about it. Kari, we'll just let the responses come in for another moment or two. All right. It looks like almost everyone has cast their vote. So we can go ahead and close the poll. So Kari, 1% are not sure. They haven't heard of it. 50% are somewhat familiar, 35% very familiar, and 16% are extremely familiar. I'll leave it back to you.
Fantastic. Oh, that's a really good spread. So this is a pretty informed audience. And as you can see, I really am playing the nerd card because I just love talking about this topic so much. I'm gonna skip the question. So good, this slide won't be controversial at all when I say that climate is changing. Can't begin to talk about ocean acidification without talking about the increase in atmospheric carbon dioxide. So to many of you, this should be familiar. This is the Keeling curve. A scientific hero of mine is Charles David Keeling, who was a Scripps researcher. He began measuring carbon dioxide in the atmosphere in 1956 on top of Mauna Loa in Hawaii. And to this day, this data set is still being collected and is the longest time series of atmospheric carbon dioxide of its kind. And it has definitively shown that the carbon dioxide atmospheric concentrations are increasing. At our present day, they're increasing at a rate a little over 2 parts per million per year, and that rate has increased. There we go. So in red on this slide here is that Keeling curve of the atmospheric CO2. So one thing to take note is approximately 25 to 30% of the carbon dioxide in the atmosphere gets absorbed into the ocean. So knowing this, it makes perfect sense that if you increase the atmospheric concentration of CO2, you're then subsequently increasing the amount of carbon dioxide absorbing into seawater. And so that green line is a time series from the Hawaii Ocean Time Series program measuring the partial pressure of CO2, so how much CO2 is in water over time, which has also increased with that atmospheric concentration. and it's mirrored again by a decrease, an increase. I'm going to get this mixed up the whole time, but it's a decrease in the pH, which means an increase in acidity. So this time series has shown that the ocean is a sink for atmospheric CO2 and that it's statistically significantly decreasing in surface seawater pH. And I also want to note that pH is on a logarithmic scale. So what this means is very tiny changes actually are really big changes. And so a 0.1 pH change is what we have historically observed as a change since the start of the Industrial Revolution. That's reflective in about a 30% increase in ocean acidity. So pH, I always like to remind people of what pH actually is and how it's calculated. It's the negative log of base 10 of the concentration of the hydrogen ion. And so these are essentially protons. And on a pH scale, we call neutral something with a pH of 1. As you decrease that number, your pH becomes lower and you become an increase in acidity. And just as reference, ocean water, mean ocean pH is around 8.1. And again, that has decreased since the Industrial Revolution. And to further hammer this home, and so while we've already observed approximately a 30% change in acidity, many models have predicted that we are likely to see an additional pH change by 0.4 pH units by the year 2100. And this is reflective of 151% change. And so there's a lot of very potentially detrimental impacts to this. So let's talk a little bit about what happens when you dissolve carbon dioxide into water. This is known as the carbonate system. So when you add carbon dioxide to water, it combines with water to form carbonic acid. Carbonic acid tends to dissociate in seawater, so it's going to break down into different ionic forms. And so this is essentially a massive equilibrium equation. So we have carbonic acid existing also as bicarbonate. I don't know if you can see my cursor, but that's the HCO3 negative, which also frees up a hydrogen ion and also further dissociates to carbonic acid, which also frees up a hydrogen ion. And so, as I mentioned, this is a big, massive equilibrium equation. When you add something like an increase in carbon dioxide, you're going to get a shift. So I like looking at this graph. This is how my brain likes to work, is as you add carbon dioxide and as you're shifting that pH to be a lower number, you're changing the amount of carbonate that is present and shifting it towards having a little less of that carbonate and more of the bicarbonate. And this can become particularly important for things that create shells. Shells are made of calcium carbonate, and this can be, make them particularly sensitive as you're getting rid of some of that ion in the form of carbonate that they very much need. And so what this means is more CO2 in seawater is making less of that carbonate available. And as you have less of that carbonate available, you are impeding that rate of calcification. And this calcification could mean that organisms are having a harder time building their shells. It can also mean in some extreme incidences, you might have a loss of shell. So the last big term that I will introduce, because this is the big one that's talked about a lot, and I thought the data in the classroom module that Amy will premiere displays it wonderfully, is the saturation state. So aragonite is one of the mineral forms of calcium carbonate that shell building organisms like oysters use. It's often expressed as an omega, and it's essentially a ratio of the amount of ions of calcium and carbonate divided by the apparent solubility product. So essentially what you need to know is when this ratio is much, much greater than 1, there is an abundance of calcium carbonate that organisms can use to build their shells. It is undersaturated when it is less than 1, which implies there's not enough of that calcium carbonate for the minerals to grow or maintain their shells. And very importantly is it doesn't have to be less than 1 for calcifiers to experience problems. So this is taken straight from the data in the classroom exercise. This is the monthly aragonite at La Push, which is a buoy that measures pH and the partial pressure of CO2 off the Washington coast. At a threshold of the aragonite saturation state of 2 or lower, you start to see oysters having trouble growing. at a threshold of 1.5, you can start to observe a larval death of those oysters. Sorry, that is my phone ringing. This is a work in progress, as everyone knows. We're all working for different offices. And so as you decrease that saturation state, you have fundamental impacts to organisms such as oysters. And you can see in the present day, there's already periods throughout the year where that saturation state are at these critical threshold levels. And unfortunately, it's projected that by the year 2100, many coastal waters off the United States, such as the Pacific Northwest and also New England, are projected to have saturation states in the surface waters below 2, in the Pacific Northwest even lower. And I just want to throw this out there as I transition to the coastal environment. Coastal environments are dynamic and they have changed throughout the day. This is data from my site here in Delaware looking at pH in a tidal creek. And you can see over the course of a month and then snapshot into a single day, you can get a pH swing of practically 1 whole pH unit. This is the day my daughter was born, so it's why I picked it. But it's a good example to show that organisms in coastal systems are already experiencing lots of change. But where the concern is that the lows could become lower and the amount of time in these lower pH waters could also increase. So I'm going to transition to coastal acidification, and how it's different than ocean acidification is the coastal acidification takes all those processes that I just mentioned, so that increase in atmospheric carbon dioxide, increasing in the ocean and thus lowering the pH, in addition to regional pressures, which are affecting the local water chemistry. I'm going to talk about 2 of the most prevalent ones. There are others, but the 2 most prevalent are eutrophication, so that's driven by nutrients, as well as coastal upwelling. And so the first one I'm going to talk about is that eutrophication, so the nutrient-caused coastal acidification additional pressures. Nutrients are fundamental for all life. It's how we're able to exist. We all depend on nutrients like nitrogen and phosphorus for our own well-being and existence. So nitrogen is found in amino acids, which are the building blocks of proteins. Phosphorus is pivotal to DNA and RNA. So without these 2 nutrients, nobody would be able to exist as we know it. However, there is unfortunately too much of a good thing. When we add too many nutrients like nitrogen and phosphorus into our coastal water systems, we get massive blooms of algae. So these are the photosynthetic plants of the ocean. They will form blooms, which are just massive, almost gardens of these tiny microscopic organisms. And unfortunately, those organisms die and sink and are consumed by organisms like marine bacteria, which respire. So things that respire, like you and I, we produce carbon dioxide as we metabolize. And so you end up getting this huge injection of carbon dioxide, and you decrease also the amount of oxygen in that process. And as we just mentioned, as you increase carbon dioxide in water, you are shifting that balance of the carbonate system. You're taking out more of those carbonate ions. You're making the saturation state become potentially lower. You are ultimately lowering the pH, and all of these combined effects can result in coastal acidification. And of course, this is amplified because eutrophication, if you look it up just for fun on your own, it's most often associated with low oxygen. And so eutrophication, this massive nutrient pulse, is associated with nuisance algal blooms. Because the waters can be stripped of oxygen during all that respiration, you can get fish kills. And again, I'll stress is ocean acidification is another conversation starter for this. When I was back in college, we didn't talk about coastal acidification. We just talked about that hypoxia, that low DO, but this has really become prevalent. So the nutrient problem comes, well, mostly from us. There's lots of different sources of nutrients that can enter our waterways. One point source way is through wastewater. We also have inputs from agriculture, from fertilizers and livestock, fertilizing lawns, nitrogen deposition from burning of fossil fuels is all sources, as well as many detergents contain phosphorus. And so I like to put this slide up because it's note that human activities have caused a lot of this nutrient injection, but individual actions or societal actions like not fertilizing your lawn before a big rainstorm or trying to avoid phosphorus-based detergents can make a big impact. And another way we can increase the amount of nutrients has been through stormwater runoff. We're increasing the amount of impervious surface we have on our landscape. So these are things like asphalt, where water cannot permeate through it, so it doesn't get a chance for the plants to use it as well. I'm sure everyone on the line has experienced at one point driving down the road during a big storm and seeing these little mini rivers that form. This is all water that's running down our drains, going into our waterways, that's been aggregating a lot of nutrients that can pulse into the system. And so one non-fun fact is that we live in a very stressful world that have a lot of different things going on. So we don't just have ocean and coastal acidification happening. We don't just have changing dissolved oxygen during these events. We have all these pressures happening simultaneously. So this is kind of a neat study that showed the juvenile quahog, or hard clam for non-New Englanders, that when you exposed it to just low dissolved oxygen waters or just low pH waters, you didn't see any significant change in its growth compared to normal conditions. But when you exposed it to both low pH and low dissolved oxygen waters, that's when you got the significant decrease in the growth. And so all these organisms are experiencing all these changes all at once, and sometimes the compounding effects of these make a difference rather than just one individual thing. And this is very hard to measure. So the second coastal acidification process that happens is by coastal upwelling. And so this is almost a forensic case study that is a lot of fun to dig and read into. Starting in the mid-2000s, a lot of oyster hatcheries along the Pacific Northwest started to observe larval oyster failures. So oyster larvae were dying, the most smallest oyster larvae were dying, and it was obviously causing a lot of problems, both for the oysters, but also fiscally. These industries make a lot of money for the Pacific Northwest, and it was a big problem. We now know, using our wonderful scientific expertise, that the cause of these oyster deaths were from low pH water. And so this is where we get to talk a little bit about physics. Is coastal upwelling along some coasts, such as the Pacific Northwest, is a seasonal process that is experienced each year. So northerly winds, so these are winds that come from the north, they can result in a net movement of the surface water to be away from the coast in the northern hemisphere. And so I'm going to show you a little bit of physics because I do have an oceanographic background and I never get to talk about the Coriolis effect in Delaware. So the rotation of the Earth applies what we call the Coriolis effect. So large-scale movements like winds get rotated to the right in the northern hemisphere. And so it's obviously, as you, not obviously, it's maybe not obvious to everyone, but if you were to throw something a really far distance, the rotation of the Earth would move it so what its trajectory would actually land at would be not a straight line. So this Coriolis force also takes effect into our surface waters, and it does something called the Ekman spiral, but it ultimately produces a 90-degree net movement of the surface water to whatever direction the wind is moving. So that's 90 degrees to the right in the northern hemisphere. And so because the water is moving away from the coast, it has to be replaced by something, and it's replaced by deep coastal waters, deep waters. So deep waters are in general higher in dissolved inorganic carbon. So this is carbon dioxide. They also can be more nutrient rich, they're colder, and they're going to have a lower pH. In the Pacific Northwest, the waters that are upwelled can be between 30 to 50 years old. I read one fact somewhere that said these waters saw the fall of the Berlin Wall. That gives any reference. And so you have these waters that have been aggregating carbon dioxide, they have a lower pH, and because climate change is into effect, that change in pH, that change in acidity has been amplifying as we progress into the future. So the waters here were already pretty low in pH, and so now we have this added effect of climate change making them even lower. And so this was sort of a watershed moment when shellfish hatcheries started observing these deaths related to the pH, but the little glimmer of hope is it offered the chance for science and industry to become well partnered together, and the Pacific Northwest has wonderful partnerships working together to better understand and help even prevent some of these processes. So a lot of the shellfish hatcheries right now in the Pacific Northwest will routinely monitor for pH. There's a few buoys that are set up that they can tune into. And so if they know that low pH water is present, you can shut your hatchery off so that corrosive water will not enter. There's also been ways to add buffers to the water to make it a little less corrosive. So adding things like sodium bicarbonate or sodium carbonate. I'm really intrigued with this current thought process of bioremediation. And so this is in some systems planting, seaweeds or using other submerged aquatic vegetations. So these are organisms that are photosynthesizing, which means they're uptaking CO2, which could help locally buffer some of these effects. And there is also efforts underway to develop oysters that could be more resistant to ocean acidification effects. So what are some of the potential effects? Why do we care? Hopefully by now I've made it abundantly clear that calcifiers, so things that make shells, are particularly vulnerable and sensitive to changes in acidity. So things like shellfish hatcheries, which are very important industries, will care very much, but there's also commercial fisheries such as sea scallops, for example, in the Northeast region. And for anyone here who enjoys eating shellfish or who enjoys going to the beach, these are all reasons we obviously care. And for mollusks such as oysters, these are larval oysters. I think larval oysters are adorable. It can mean that low pH water might result in a higher mortality. For adults, it might not necessarily mean mortality. It has been shown that they grow slower. But if you are spending your energy and time devoted to maintaining or building your shell, you are spending less time on other key activities such as eating and reproducing. So it will have other ramifications down the line. And so here are just a handful of other studies that I've come across that I've found really fascinating that again show it's not just about mortality that will have effects in the ecosystems. And so mussels have been shown that they're byssal threads. So these are those little kind of threads that allow mussels to stick to rocks. Under high CO2 conditions, those threads become weaker. So one thing that is been established in the literature is for sharks and fish, the olfactory systems can be impacted. And so, for example, clownfish might have a more difficult time finding their way back to the anemone, that's their home. They have a more difficult time being able to follow the chemical cues off of these different, ecosystem types. And I thought this one was very interesting as mussels lose their color under high CO2 treatments. There are a bunch of other really fascinating studies. I didn't talk at all about corals, but corals also have been shown to have a potential decrease in calcification and also be more susceptible to things like coral bleaching because we're also having warming take place. So this is where I empower everyone because there is a lot of things that are not understood yet. We understand the water chemistry, that's not debatable. We know that when CO2 enters water, it does the carbonate system breakdown, but there are a bucket list of things we need to know. The two papers that I have featured there are two papers the Mid-Atlantic Coastal Acidification Network put out last year that was just establishing, hey, this is what we need to understand. These are places we need to monitor because we need more information. So all of the future scientists or current scientists on the line here, we need to know what the future impacts will be. We need to know current day local and episodic acidification events and where they're occurring. We've talked a lot about single organism impacts, but how will that impact the whole ecosystem? How are multiple stressors like changing salinities also affecting it? Are there some organisms that might be able to have a better adaptation? There's many more things we don't know. So with that, that is the end of my section. I put my email out there. If anyone wants to go into more detail about anything I showed or have any additional questions that don't get addressed here, you can feel free to email me and I'd be happy to talk to you. So I will send it back over to Jen to transition to.
Yeah, if you don't mind, as we're Moving on to Amy and this new data in the classroom module, there were a few questions that might be good to just clarify before we dive into this educational tool. So one was concentration of carbon dioxide in the ocean have a limit, or is the ocean an infinite sink?
That is a wonderfully fantastic question that I don't know the definitive answer to, but I think that that is a wonderful question, but I can say this is under our current modeled projections to 2100, the ocean can absolutely handle the amount of CO2, not for the better. So in the immediate future, the answer is no, but I don't know if there is a threshold. I would think we might have bigger concerns if we ever hit that threshold, if it exists, but I'd have to follow up with that.
Great, we can do that. And one other question, sort of touching back on the eutrophication piece. Doesn't the formation of an algae bloom consume carbon dioxide from the water? And when the organisms eventually die, the respiration of bacteria feeding on the dead algae just replace the carbon dioxide consumed by the algae, so that there's no net change. What am I overlooking?
Gotcha. That's a fantastic question of something that I didn't really go into. So thank you to whoever asked that. So one of the big processes that happens is that algae, yes, they're taking up CO2, but when they die, they're sinking. And so a lot of the respiration that happens is in the deeper waters that might not have the ability to reach that atmosphere. So we have stratification that happens. And so it's typically in the more bottom waters of the coastal system where things like clams and shellfish often are, but that's the primary difference is it's happening kind of on the deep end of the swimming pool, whereas the photosynthesis is happening at the top where it can readily exchange with the environment. So it almost gets trapped in the water.
Great, thank you for clarifying that. Yeah, I feel like hopefully that answered some of those science questions related to coastal and ocean acidification. And we can now move on to Amy's presentation where she'll be sharing about this new data in the classroom module. So Amy, take it away.
Okay, thank you, Jen. Well, I thought we would just kick off the second part of the presentation with an audience poll. So actually, Jen, I'm gonna kick it back to you so we can take the poll.
So Amy, it looks like there has been a technical difficulty, so I don't think that poll now exists.
That's okay. We'll just move on. No big deal whatsoever.
Thank you.
All right. Actually, my screen is not advancing. Or my presentation is not advancing for some reason. Here we go. Okay. So I wanted to start off just giving a quick background on data in the classroom. I know that at least half of you guys are both formal and informal educators. And data in the classroom was developed to help teachers bring real-time data from NOAA into their classrooms. So currently there are 5 modules on topics like El Nino and coral bleaching. Most of these are aimed at middle school level, with the exception of the ocean acidification module, which was developed for high school students. And all of these modules offer the same resources. So that includes a teacher's guide with lesson plans, the web-based student activities, and access to interactive data tools. The modules all have the same pedagogical approach as well. So there are 5 scaled levels of interaction in every module, beginning with relatively basic teacher-led discussions and lessons on how to read and interpret graphs. That would be level 1. And building towards lessons that challenge students to access data themselves and investigate a question. And that would be levels 4 and 5. So what I wanted to do with you for the bulk of this presentation was to explore the website and the online platform for students and complete just a few sample activities together. So here we are at the data in the classroom website. And first, I'm going to show you some of the teacher resources. These contain a teacher guide containing the lesson plans for each level. That's on your left. Some optional paper and pencil worksheets that go with the online activities. That's in the middle. And alignments to high school NGSS performance expectations, and that's on your right. So now we're going to go back and I'm going to launch the student activities. And when you launch, you find the guiding questions on the introductory page. So in this case, the guiding question is, carbon dioxide in the atmosphere is rising, but what does this mean for the world's oceans? Levels 1 through 5 contain the student activities as well as a Get Data tab where you can find a one-stop shop for accessing all of the data tools in the module, and a page for you to download the lesson plans and the student worksheets. So we're going to start with a sample activity from level 1. You'll recognize this graph from Kari's talk showing changes in atmospheric CO2 in red and ocean CO2 in blue. And here the goal is for the students to make a prediction about how rising CO2 impacts ocean pH. And depending on your class and your students, they may not know much about this yet. So they'll have to draw on whatever prior knowledge they have. But they can also explore the information and the illustration that's accessible on this page. So I'm going now to the live website. So bear with me for a moment here. And so now we're on the live website, and I just want to demonstrate some of the features. So in the window here, your students can interact with the graphs. You can scroll their mouse over the data points, click in the legend to turn data layers on and off, and they can use the features below or above the graph to zoom in to specific time periods like this. Okay. And I just mentioned the additional information that students can access in order to make their predictions. So I'm going to show you that here. Again, you saw this in Kari's talk. So if they're unfamiliar or need to remind themselves about the basics of the chemistry, they can check this out. All right, so I'm going to take us back to the presentation. All right. So if you are a teacher, I want to point out that there are optional paper and pencil worksheets for each level. So in level 1, the worksheets have students make written predictions using sentence starters. There's sentence starters to help them explain their predictions as well. And they also have to illustrate predictions on a graph. So this is just an example of some student work here. When students move to level 2, they'll compare predictions they've just made to real pH measurements. That's shown in green. And then there are questions in each level that help students identify key information and concepts from the data activities. So here they are. Go ahead, see if you can quickly answer one or both of the questions on your own. And then you can see how you did. Okay. And I'm going to move us on into level 3. Here, students explore additional processes that can impact ocean chemistry closer to shore. And they do this to begin with by running and interacting with an animation. I'm not going to run the animation with you here, but it does cover the 2 key processes that Kari talked about in her presentation, both eutrophication and upwelling. I'm going to take you to the data activity in this level, which transports students to the coast of Washington, where they will gather data from a mooring. And this is one mooring that NOAA's Pacific Marine Environmental Lab has established in collaboration with others. And there are many other moorings around the country that have similar data sets that you and your students can access that might be closer to home. And you can find a link to these in the Get Data tab. The coastal ocean pH graphs from these moorings can be a little tricky to interpret. So your students are going to access them here. They can open up the graph. I'm going to show this to you now. And one thing that you'll probably notice right away is that data has gaps. There are occasional sensor failures, and the equipment is removed for maintenance during the winter months. So that's one key feature just to potentially have a discussion with your students about. One thing I want to draw your attention to on these graphs is that they're 2 annotated data points. So students can scroll over these points to help them interpret the large seasonal changes in pH. And what students are asked to do in this activity is to focus on the range of values over the time series. And then they're asked to compare this to the range of values in Hawaii over the same time period. So let's go ahead and do it. You're looking at open ocean pH off the coast of Hawaii on the left, compared to coastal ocean pH off the coast of Washington on your right, from 2010 to 2017. So what's the difference in the range of values over the 7-year time period? I'm going to highlight the range for you with these orange dotted lines, and I'm going to pause so you can take a moment to quantify the range on your own. So you might have noticed that there's a range of about 0.05 pH units in Hawaii, from about 8.05 to 8.1, compared to about a range of 0.5 pH units in Washington. So from about 7.9 to 8.4, a huge difference. And students should be able to conclude that the ocean pH near the coast of Washington shows more variability and more extreme highs and lows. And the goal is for them to identify the possible causes for these differences. One thing that your students may wonder about is, what's the long-term trend in pH at this site? Is it declining in the same way that it is in Hawaii? And because of the relatively short time period of this data set and the high variability, it's just not possible to determine this yet. As Kari said in her talk, there's just a lot we don't understand yet. However, scientific models do show that during certain times of the year, coastal ocean pH does fall outside of what's quote unquote normal. So in other words, seawater is at times becoming more acidic than what marine life are used to. And this leads us to level 4, where students will investigate data associated with impacts to marine life. So here we're going to pause and take our last audience poll. So take a good look at the image, and I'll hand you off to Jen.
How about we adapt a little bit, and folks can take this moment to just type into the questions box, what do they think these are images of? We'll give you a few minutes. All right. Got, oh yes, a variety of answers coming in. We went from a multiple choice to many options. Amy, some of the answers include oyster larvae, plankton, bivalves, clams, rotifers, diatoms would be more specific in the plankton category. And I think, oh, dinoflagellates, we've got some very specific plankton. Foraminifera and potato chips, I think referring to pteropods. And I think that covers most of what came in. Thank you all for
Great.
chiming in.
Well, those are actually really good guesses. And the folks that were guessing larval oysters, you got it. That's right. Let's see. Okay, so this takes us into level 4. And what students will be doing in this level is trying to figure out how acidification is impacting oysters, particularly larval oysters off the coast of Washington. So first, your students can learn, or they can be reminded about how to read and interpret box plots here. And so you can see they can click on that one spot on the left-hand side that says, what is a box plot? And they'll get a nice description of how to interpret those box plots. And then they're likely need a little bit of help getting oriented to the data in these plots. So aragonite saturation state is on the y-axis. On the x-axis are all the observations that are binned for each month. And the boxes and the whiskers show how spread out the observations are for each month. So the question for you guys and for your students is, do the current conditions in Washington support the growth and the survival of Pacific oysters? And to find out, we're going to click on the blue adjustable line. And let's see. Hold on, I'm going to take us over to the live website to do this. Okay, so you can see that this blue line is adjustable. And I'm going to take this blue line down to the 2. Okay. 2 represents the threshold that Kari mentioned. And that is when aragonite saturation states are less than 2, larval oysters have trouble growing and building their shells. So if you look at the pie charts above each month, you can see when larval oysters may not have enough aragonite to grow and build their shells. So for example, you can see that in January, 100% of the observations fall below the threshold. And in November, 80% of the observations fall below the threshold. So seasonally, especially in the winter months, larval oysters are exposed to conditions that are not optimal for their growth. And since I'm on the live website now, I think I'm just going to quickly show you level 5 without doing too much more than just giving you a bit of a tour here. This gives students opportunities to design their own investigation related to soft shell clams in the Gulf of Maine. And you'll see a map pop up here where students can access the data from Hawaii, Washington, and now the new location in the Gulf of Maine. And then I'm going to take us over to the Get Data tab, which has all of the data and the data tools, including some models that I didn't have time to show you. And this is here for you if you want to develop your own activities for students and provide them with access to the data. So with that, I am going to wrap up. And if you're interested, I'll encourage you to join the Data in the Classroom online community by signing up for the newsletter. That's on the website. And then if you're looking for something shorter, a short mini lesson for your students, I'll really encourage you to check out this animation. I just mentioned it briefly. It was at the beginning of level 3. It can serve as a standalone resource for you in your classrooms. It's totally interactive, and you can find the whole animation on NOAA's Ocean Acidification Program website. And I'll end there, and happy to answer any questions from the audience.
Thank you so much, Amy. I know there have been questions before we move into questions from the audience for both Amy and Kari. This is being recorded, and the video and along with the PDF of both Amy and Kari's presentation will be made available. So you will have those as resources. Additionally, we will be sending these URLs that were shared for Data in the Classroom, this coastal acidification animation as well when we follow up likely early next week. So just to put those questions to rest, so we can now dive into questions about this Data in the Classroom module or about some of the science that Kari presented. So we know we have questions that have come in. If you haven't had a chance to type your questions in, you can do so now in the questions box at the right-hand side of the screen. And so this is, we'll open with one that we'll go back to a question about the science just to start. That is, with more carbon dioxide going in the ocean, is it more likely that more will also be mixed at the boundary layer back into the atmosphere? And Kari, that, you know, that likely be a question for you.
Sure. So I think I took myself off mute. So as more CO2 go into the ocean, so is that suggesting that some of the CO2 then comes back off the ocean into the atmosphere? I think I'm interpreting that question.
That's my interpretation.
And if I'm wrong, you can correct me, whoever asked that. So there's, I think, of course, the ocean's variable. So anything that me as a scientist like to say is always like, yes, but depends. So that value of about 30%, that is the ocean's net sink of taking in the carbon dioxide. So of course, the ocean can also give off carbon dioxide in certain situations, in certain places, but overall the net is that about 30% of that CO2 will continuously be absorbed. So I know that kind of is like dodging the answer it, but so there are spots where you could have biological processes that might produce carbon dioxide that might be able to come off, but in general, that 1/3. In terms of the coastal upwelling, so as water is circulating throughout the ocean, the concentration of carbon dioxide in the atmosphere is then getting pulled to those deep waters that are removed from the atmosphere. They continue to aggregate carbon dioxide as things in the deeper waters are getting respired. And so that's where you get a lot of that carbon dioxide accumulation, and where you have that upwelling process become really detrimental, because now you have waters that are very high in CO2 and can be additionally detrimental. So I'm dodging that. If you want to ask for clarification or email me, I might be able to provide more insight.
Thank you, Kari. Amy, I believe this is a question that's focused on the data in the classroom module. One was, is there any, I know you pulled out some of the buoys that were working. Are any of them in the Alaska region or Arctic?
I would have to check to be sure, but from what I remember, I believe that there are. Yeah.
Great. Okay. Thank you. So, and I know a few more questions are coming in. We will provide the information about getting onto the NOAA Data in the Classroom listserv and all of that afterwards. Also, other folks are sharing some resources that they found helpful in teaching about ocean and coastal acidification, which we welcome. Please go ahead and email those to the email noaa.oceanacidification@noaa.gov, and we will add those so that all the participants that joined us here today can have access to those. And yes, this will be posted on the NOAA Ocean Acidifications Program YouTube channel as well. So you can tell Kari and Amy that people are hungry for this information and will use it because they are wanting to know that they can refer back to it and look into it as they incorporate it, hopefully in their classrooms or in educational settings. So getting back to some of those content questions, another one, we'll go back to the science. So are there estimates of the impact of submarine groundwater discharge on ocean acidification? How much can blue carbon sinks such as seagrass meadows handle?
Great. So I'll take that as two questions. So I don't know the answer to the submarine groundwater question, but I know that there are papers that are looking to address and or model that question. So if there's digging to be done, there is somebody who has also asked that question and is actively trying to find some of the answers for that. So for blue carbon, so for anyone who's not familiar, blue carbon is the term used for the amount of carbon that can be sequestered and stored by coastal ecosystems. So these are tidal wetlands, mangroves, and submerged aquatic vegetation, and are a great potential opportunity to be able to preserve our wonderful natural coastal environments while being able to sequester carbon dioxide. And so those are by nature coastal systems. They can already right now sequester and store a lot of carbon. There are ways to increase the potential for them to store carbon. Where I often like to look at the picture is losing wetlands, losing mangrove forests, which I know depending on where you are, they're encroaching on tidal wetlands, but the loss of these blue carbon habitats to me is what's detrimental, because that's a loss of a sink for these carbon dioxide processes and a potential re-release of some of the already stored carbon. And so that's my first thing, is it's more of making sure we're not losing that benefit, and then looking at opportunities to increase the amount of carbon. So the last tiny thing I'll put in for a lot of these systems, it's more looking at taking up the atmospheric CO2 or minimizing the amount of, you know, nutrients also that can be injected into the environment. One of the ways to do that is looking at changes of salinity and different methane, so going into a whole nother gas, and optimizing or decreasing methane outputs from tidal wetlands by increasing salinities for certain managed ponds. So the answer is blue carbon is a great tool, but where I personally become more concerned about is losing that tool rather than necessarily having it be what can solve all the problems.
Thank you, Kari. Amy, going back to data in the classroom, somebody would love to know, what background do high school students need to handle the data in that module? Chemistry, math, biology?
Great question. So I teach environmental science and biology. I would feel comfortable introducing this with my students. And of course, they'll need a little bit of help with the chemistry if they haven't taken chemistry yet. But they certainly are able to handle it just by using some of the resources and the schematics in the module. I think students are perfectly able to get the basics behind the chemistry. So I would say any level in high school would be appropriate.
Great, thank you, Amy. One other question related to probably not just this module, but in large. Amy, do you know of any other topics planned for this module or others in data in the classroom?
That's a great question. I can't answer that at this time. There certainly are ideas out there, and if you have specific ideas, the folks in the audience, send them our way, and we'd love to hear from you. Yeah.
Great, thank you. And I think this is a great one, just being mindful of time, we'll wrap up on, and I think you possibly can both speak to it. You mentioned in some ways people impact coastal acidification, such as fertilizers, burning of fossil fuels. Do you have meaningful, specific stories or examples of ways students can mitigate coastal or ocean acidification?
I can speak to that in regards to the NOAA's Ocean Acidification Program's animation that I referenced in my presentation. So the animation the first part of the animation spends time connecting students with the science of coastal acidification. And then the last piece is very interactive, and it helps with exactly that, talking about how students can mitigate, what they can do specifically. Yeah.
Great, thanks.
Sorry, I'll also echo what Amy said. Is I think that module did a really good job at showing some of the individual changes that we all could make to reduce the nutrients concentrations. I know for me is I try my best to use detergents and things that don't contain high amounts of phosphorus. I know that there are a lot of products that used to contain a lot of phosphorus that aren't available anymore because of these environmental concerns. So this is my small story that I'll tell. Is I'm somewhat of a geologist. We use products to disaggregate clays in some of our sediments. When I was an undergraduate student, we used Calgon, the powdered bubble bath, to be able to disaggregate clays to make it easier to sieve them. This last summer, I had an intern and I told her, go get Calgon, it would be great. And apparently that product is no longer available because it was detrimental to the environment. And so that was a watershed moment for me, being like, oh, this is great that this product's no longer available, but also now I have to buy it through Fisher Scientific and have it be much more costly, which is fine. But that was something that caused me to realize that I was doing things that were potentially adding pollutants through nutrients into the environment. But there's also, to make the biggest bang for our buck, it's looking at things that we can all do societally. And so looking at upgrading wastewater treatment plants to have tertiary treatment opportunities or not to have combined sewer overflows happen as often. And so those are things that are maybe beyond our individual control, but societally potentially on the table.
Great. Thank you so much, Amy and Kari. Thank you for the excellent presentations. I know it has sparked a lot. We've gotten some great thank yous and ideas sparked and great conversation in the chat box. So thank you so much for that. Thank you to all of you who joined us. We really appreciate it. And yes, the thanks are just hollering out. So as I mentioned, the PDFs of the presentations of Kari and Amy's presentations, along with the video of it, will be shared early next week. So you all will get access to that. We will also, in our follow-up email that you will receive tomorrow, we'll get all of the links for the NOAA data in the classroom. How do I join the listserv? Where was that coastal acidification animation? All of those links that were mentioned will show up, arrive in your inbox tomorrow. And I encourage you all, we've had some great, this is what this webinar series is intended to do, is build the ocean acidification education community. And I know a lot of you have great resources you use, so please email those to either myself or Laura, or the email that you got this registration link from, so that we can add those. We have a whole list of resources that we make accessible to folks who participate in this webinar, and also add them to the NOAA Ocean Acidification Program website. So please share those. Yeah, and thanks again, Kari and Amy, for excellent presentations. We will potentially have our next webinar in late spring, and you can check out the source website for those. And here is the data in the classroom link if you want to dive in, if you're excited. You can do that now. And I think with that, one more thanks, Kari and Amy, for sharing your time, your expertise, your energy, to all of you who joined us, and the great questions and ideas that were shared. And with that, we will wrap up and hope you each have a great day.